Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking a little bit about Hess's Law, but before we can talk about Hess's Law, we have to define what enthalpy is. So enthalpy is capital H, and it is the total heat content of a system. The nice thing about enthalpy is that enthalpies have been tabulated in enthalpy tables. So you'll find them in the back of most chemistry books, you'll find them online, worksheets, all over the place. But the way that they are kind of laid out is you'll see something that says H of F, or sometimes delta H of F, but it's the enthalpy of formation of different substances. So this is the total heat content of manufacturing these different compounds. And so you'll find them, though, again, like all over the place. And sometimes they will vary depending on what your source is. So you want to make sure that you use whatever table it's asking you to use, just to make sure that you're using, again, the correct source. So first thing you need to know, if you're calculating the delta H of something, so if we're calculating the change in enthalpy for a reaction and it's less than 0, that means that the reaction is exothermic. So remember, exothermic means to release heat. And so that means that our system is losing heat. On the other hand, if you calculate a delta H and you get something that is greater than 0, that means that your reaction is endothermic, which means that it is absorbing heat. So now that means that you are gaining heat. So what about enthalpies of formation of elements? So what if we're talking about just nitrogen or just oxygen or hydrogen or just, a piece of graphite, pure carbon? So enthalpies of formation that you see in tables, normally it excludes pure elements, because how much energy does it take to make a pure element? Well, we're talking about nuclear reactions at that point, right? We're not talking about really heat content changing. So enthalpies of formation of elements in their standard states are defined as being equal to 0. And so that's just kind of like a standard way of making everything equal. And so you'll see a lot of times that pure elements are excluded from enthalpy tables. Now, what is the unit for enthalpy? Normally, it's in kilojoules per mole, or sometimes you'll see it in just kilojoules, because the reaction that you're looking at takes care of the equivalency of moles. So even here, you can see that it says kilojoules per mole. So now we can talk about Hess's law. So Hess's law states that enthalpy is not dependent on a reaction pathway. In other words, to get from A to B, it doesn't matter how many steps it takes you to get from A to B. As long as you start at A and you end at B, everything is equivalent. So in other words, if we take the enthalpies of the products and we subtract the enthalpy of the reactants, no matter how many steps it takes us to do that, they will always be equal to each other. And so a good way of looking at that is this. So we can see that in this picture, we have enthalpy here in kilojoules. And so what we're doing is we are taking nitrogen gas and oxygen gas and reacting them in order to make nitrogen dioxide. So here we have a two-step process. So we're taking nitrogen, we're taking oxygen, and we are manufacturing an intermediate, which is nitrogen monoxide. And so then I'm taking that nitrogen monoxide and oxygen, and I'm reacting it together to get my nitrogen dioxide. So if we are looking at, a two-step process, it costs me 68 kilojoules of heat that is being absorbed by doing this process. Now, again, if we instead look at a one-step process, look, still 68 kilojoules. So it doesn't matter if I take 2 steps to get here, or if I take 1 step. The actual amount of energy that was absorbed is exactly the same. So notice this is an endothermic process, this is an exothermic process, but if I add them together, I get my exact product, which still has the same amount of heat content that was absorbed. So what are our rules for Hess's law? The first is that you have subreactions. So if a subreaction is multiplied by a coefficient, then you multiply the enthalpy value by that same number. So for example, if it's 50 kilojoules to do something, but I have double the amount, then I would double the amount of enthalpy that it would actually have. And that just kind of makes intuitive sense. Now, something that also sometimes makes intuitive sense, but it's a little harder to picture, is what if I'm doing the reverse process? So what if the table says, hey, here's how much energy it's going to take these two things and put them together to make this one thing? What if instead I started with this one thing and was breaking it apart into the two original substances? If I do that, what I do is I switch the sign. So if it was a positive 50 kilojoules, I would then change it to a negative 50 kilojoules because I'm doing the opposite process. So again, here's a good example of that. So I've got CO2. Again, I have carbon in its standard state. I have oxygen in its standard state. And so that is 393.5 kilojoules per mole. What I have here is I have methane. I have, again, carbon in its standard state. I have hydrogen in its standard state. That's 74.6 kilojoules, right? And then right here, this last step is negative 484.3 kilojoules. So notice that if I add these three things together, a lot of these things start canceling. And when they cancel, what that's showing me is that this is my overall reaction. So what I can do is I can just add up the enthalpies of these individual items, and I can end up getting a total energy change. So even though this was 393.5 kilojoules, this was 74.6 kilojoules, and this was negative 484.3 kilojoules, if I add them all together, I get an overall change of negative 16.2 kilojoules. That means that this overall reaction is exothermic. Now, let's do an actual example. So here are two reactions, and here is the actual reaction that I'm interested in. So these are, again, called sub-reactions because you can add them together, subtract them, multiply by different things. But the whole point is I need to take these two and I need to turn it into this. So I'll show you how I can use Hess's law to do that. First thing I always like to do is I like to point out one thing in the actual equation I'm interested in and find it in the sub-reactions. So let's say we focus on iron 2 oxide. So I see iron 2 oxides here. Now notice iron 2 oxide is a product in this reaction, but it is a reactant in the reaction I want. So what I can do is I can flip this reaction so that I have this as my reactant and these as my products. Now remember, what do I do in that situation? I flip the sign of the enthalpy. So what I do is I flip everything around and then I change the sign so that it is a positive number. Now, another thing that I did is I multiplied this then by 2. Why would I need to multiply everything by 2? Because this has 4 FeOs and this only has 2. So notice that not only did I make this positive, I doubled the amount of enthalpy that I have for this reaction. So instead of negative 544 kilojoules, this is positive 1088 kilojoules. Because again, I doubled everything and I flipped the reaction around. Okay, now let's find another object. So here is a product. Here it's still a product. So if I take that and just directly take it from the reaction, just write it exactly as it was, I would take negative 1648 kilojoules. And so now what I have is I have two sub-reactions that I can start to add together and see if I get this. So notice Fe, Fe, those go away and they do not appear in this reaction at all, right? So since they don't appear in the reaction, they should cancel. Now, also, I have 2 oxygens here. I have 3 oxygens on this side. So notice I'm not canceling out the oxygens. I have 1 left over. So I try to do my best to kind of cross out this 2, but then to leave this one so that I have only 1 oxygen remaining. And notice in my reaction I actually have here, I have 1 oxygen that is remaining. So in reality, my overall reaction is FeO, so 4 of them, exactly like this, plus an oxygen, exactly like this, yields 2 iron 3 oxides, which is right here, which means that if I add these together, I now have my overall enthalpy change, negative 560 kilojoules. So what do I know about this reaction? The process of turning iron 2 oxide to iron 3 oxide is exothermic. All right, so hopefully that made sense. If you have any questions, let me know.